Hi, I'm Miss Hearn. Let's get started.
We're going to find the inverse of f of x equals the square root of x minus 1. We're then going to graph f and f inverse on the same axes, and we're going to state the domain and range of each. We should see that the domain of f is the range of f inverse and vice versa. Step 1, what was step 1 for finding the inverse of a function in the 4-step process?
Hello, can you hear me?
Hi, I can, yes.
Okay, so the first step is to replace f of x with y.
Very good. So we're going to replace f of x with y, and we're going to get y equals square root of x minus 1. Now, before we move on to step 2, one of the things you're going to want to keep in mind with these more complicated problems is their domain. For example, here, y equals the square root of x minus 1. What x values are we allowed to plug in? Or give me an example of an x value that I'm not allowed to plug in that would cause a problem. Okay, -1 would definitely cause a problem because if we plug in -1, we get a -2 under the square root.
What about 0?
0 would also cause a problem. That's right. 0 minus 1 is -1. We won't, although we know how to take the square root of a negative using complex numbers, it would get the number I. We are working with functions where we're only interested in the real number solutions. So we're only working with real numbers. If you want to find the domain of a square root function, all you have to do is take whatever's under the radical, called the radicand, and solve the inequality greater than or equal to 0. So in this case, we want x minus 1 to be positive or 0, and that's going to happen adding 1 to both sides when x is greater than or equal to 1. Okay, so as I work through this problem, I'm going to keep that in mind. I'm going to actually make a note of that here because it's going to be important when we're switching x and y values. So the next thing we're going to do is we're going to switch all the x's and y's. That's step 2. So wherever I see a y, I'm going to put an x. Wherever I see an x, I'm going to put a y. But also notice what that means for our function. We've changed our function. So now the y values always have to be greater than or equal to. So I'm going to make a note of that. Okay, now step 3, we're going to solve for y. Right? How do we solve for y in a square root equation like this? What do I have to do? Square both sides. Very good. So we're going to square both sides to get that y out from under the radical. Okay, so when I square both sides, I'm going to get x squared equals y minus 1. And then I still have to get y completely by itself, so I'm going to add 1 to both sides. And I'm going to see that y is equal to x squared plus 1. I just want to point something out here. It makes sense that the y values have to be greater than or equal to 1, because if you think about it, the smallest number you could get for this function is if you plugged in 0 and added 1. So it makes sense that y would be greater than or equal to 1. All right, the 4th step is that we're going to replace y with f inverse, and we get x squared plus 1. Okay, but what is the domain of this function going to be? In other words, in the original function, what was the range? Well, I'm going to go ahead and the next part of the problem rather is to graph these on the same axis. I'm going to go ahead and start by graphing our original function. F of x equals square root of x minus 1. So that's going to look exactly like square root of x. Remember what square root of x looks like. It looks like this. It goes through 0, 0, it goes through 1, 1, and it goes through 4, 2. It's going to look exactly like that, except shifted how?
To the right.
To the right one. Good. Remember, whenever it's inside the parentheses, inside the root, it's going to be affecting the x, so it's side to side. And whenever it affects the x, it's going to do the opposite of what you expect. So when we see -1, it actually moves everything to the right one. So the x coordinate's actually going to increase by 1 each time. So 0, 0 moves to 1, 0. 1, 1 moves to 2, 1. And 4, 2 moves to 5, 2. So we're going to go through 1, 0, 2, 1, and 5, 2. And it's going to look like this. Okay, so that was the original function, square root of x minus 1. What is the range of that function? Looking at the graph, what would the range be? So range is referring to y values, right? So from lowest y value to highest y value, what is the range of that red graph?
Would it be 0 to infinity?
Very good. So in other words, y would be anything greater than or equal to 0. And that means that when we switch the x's and y's for our inverse function, the domain has to be only x's greater than or equal to 0. So actually, when we have to keep that in mind when we're graphing the inverse function. The inverse function is x squared plus 1, but that would be a whole parabola. And in fact, it's not going to be the whole parabola because since the y values were restricted in our original function, the x values are restricted in our inverse function. So yes, we're going to be graphing x squared plus 1, but only that piece of it that the x values are greater than or equal to 0. So let's go ahead and try that. All right, so we're graphing f inverse. What is the parent function for f inverse of x equals x squared plus 1? What function is it related to that we've memorized the key points for? Do you remember? I'm going to show you where to find our library of functions. So if you look through all of our lecture notes, there was a library of functions page. So here's our library of functions. Which one of these is our graph related to? Very good, the square function. Okay. This is going to be just like the graph of f of x equals x squared. Graph of f of x equals x squared goes through 0, 0, it goes through 1, 1, and it goes through negative 1, 1. It's going to look just like this graph, except how are we changing it? It is going up 1, that's right. In other words, all of the y values of all the coordinates are getting increased by 1. So it's going to go through negative 1, 2, 1, 2, and 0, 1, shifting up 1. Except for one thing, we're not going to be using any values where x is negative, right? We're only going to be doing the right side of the graph. So we're going to go 0, 1. And then we're going to go to 1, 2, and it's going to look like this, only half. Notice if I had the other half, it would not look symmetric. It would not be a mirror image across the line y equals x, right? So it makes sense that we had to restrict that domain to just positive values so it matches up to the original function. It also is interesting to observe that if you look at any pair of coordinates on one of the graphs, the switched pair is on the other graph. So the green graph goes through 0, 1, the red graph goes through 1, 0. The green graph goes through 1, 2, the red graph goes through 2, 1. And in fact, I don't have it labeled, but since the red graph goes through 5, 2, that must mean that the green graph goes through 2, 5. So this is probably the most challenging type of problem, well, second most challenging type of problem to find the inverse because you have to remember to restrict that domain. But there's a couple different ways to remind yourself, and one of them is to look at the original graph and see before you start trying to graph the other one if there's any restrictions.
I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the video. In our next video, we're going to look at how to determine if a function has an inverse.